run. But I'm now recording. So this is what we're going to be trying to do for the next 15 days, at least foreseeable future, what we've planned for, this kind of alternate school. We're making changes as best we can, as fast as we can, and hopefully able to adjust and get some good content and some good learning out there still. We're starting with Unit 5, which is going to be comparing functions. So luckily, this isn't new necessarily. We're looking at stuff a little differently, but it's not brand new. We've already talked about, before I even got there, linear stuff, linear equations. Then we talked about quadratic equations when I started. And then we did exponentials, and now we're going to kind of compare all three and show you how to compare all three. So what they are isn't new, but how we're approaching them is a little bit different than normal. My plan, hopefully, fingers crossed, is to be able to fit a quality lesson in 30 minutes. I think if there's not a lot going on with classroom stuff, management and things, I think a 30-minute lesson's fine. And if I can get that done, it'll be great. We have the chat box that I can always read and have you. Let me rename you real quick, Freddie. So that is Freddie. All right. Where was I? Oh yeah. So again, 30-minute lesson. It'll be exactly what's on there in Canvas. It's posted right now. And what I want, it's all in Kami. I get that. But I also want to say that it's not all due. Okay, so typical like our packets were and our lessons were back in class, we would have notes, fill in the blank notes. And then at the bottom of the notes or the back page, we would have a couple of problems to do. Okay, so we're not going to have anything added tomorrow. Okay, maybe like a Monday, Wednesday, and we'll come in Friday, answer a bunch of questions, and do some stuff. Okay, so it's not going to be like 30 minutes every day or an hour every day of stuff. I think you have a lot going on at the moment, and we're going to start slow. We're going to start slow and then go forward. And if we can handle more, and if I need to put out more stuff, we absolutely can. And you know, as things go along, we'll kind of see. But it's in Canvas right now. It doesn't pop up when you click the link because it wants you to open it in a new window, which is fine. It gives you more room to write on it through Kami. And you'll be submitting it just like normal through Kami. So again, the first part is going to be notes. The back part is going to be some problems. So basically what's going to happen, it's going to be due midnight tomorrow. So you'll have all day today to watch the video. If you leave in the middle of the thing and you want to come back to it, it will be posted. So you have all day today and tomorrow to watch a lesson, kind of fill in some notes. I'm going to also post a discussion board through Canvas. It'll be on there where you can just put all your questions. You can just send your questions to me and I can respond to them. So throughout the next couple of days, if you don't, it can kind of consolidate everywhere all our questions are coming from, and then I can come back live and or just record a video of me answering them all real quick. I'm not going to do an afternoon session today because of how new this all is, and I don't want to overwhelm you with a bunch of stuff. So we'll get right into it, and then my plan is eventually to go back live in the afternoons. If you join, great. If you can't, it's okay. As like the support time, if that makes sense, so we can answer some questions and whatnot. So without further ado, with all the announcements out of the way, and I'll kind of post the announcements around and just stay flexible with me as we're trying to figure all this out. So it would help, I think, if you opened the document. Again, you can kind of flip back and forth. Let's see here. You can kind of flip back and forth. But one of the big things is I'm going to be talking a lot, and so if you want to flip over to it, fill in some stuff, flip back, that kind of deal. All right. So I'll go ahead and start though. I want to have three things up. We'll have linear functions. We have quadratic functions and exponential functions. If you look on the Canyon work, it has kind of like this T-chart. Okay. Now, one thing. Oh, excuse me. Hold on. So linear, quadratic, and exponential. What the little T-chart or the little chart does in the document is it has the name of the function, general shape, and then a sketch of it. So I want to talk about these a little bit, kind of draw a little bit of stuff, and let's put these guys in the in here. Okay, linear, quadratic, and exponential. Now there was a little shortcut that kind of helped me with linear. You know what that was? The word line. Obviously, all of these are lines, but it is a straight line. Let's see. Let me turn off the waiting room. Okay. Isabel, we are doing this twice a week, and Friday is like a bonus day. And I'll also come live in the afternoon. Good question. If you find the chat box, I can answer your questions. So what we're gonna do now for all of Unit 5, the next 2 weeks, we're gonna be comparing linear, quadratic, and exponential equations. What they mean and what they look like, all of that. For some reason. All right. It'll admit camera. So linear, general shape of the graph, I would say it needs to be a straight line. It's very important. It needs to, a sketch right there, a straight line. It needs to be a line. Now, with those, the typical line, the stuff that before you got to algebra, we threw some squares in the picture and some crazy variables. We thought of a line, and that's what a line was. It was linear, okay? And there's a couple forms for that, but one of them, I think the most familiar form is slope-intercept, so y equals mx plus b. I think that's the most familiar with linear equations. And they're simple, they're straightforward. You plug in a number, multiply a little bit, add some stuff, and kind of, it's also how we know, up and over, or it's how we know to count for slope. It's the most basic and simple thing that we've learned about, right? Okay. Quadratics through curving things, through a wrench in the system, because they're curved. They're U-shaped. And again, a sketch obviously would be a U. It's why they're U-shaped. And we knew the standard form. We know now that it's ax squared plus bx plus c. Y equals ax squared plus bx plus c. Those are our quadratics. That was when the problem started happening. That's when it got annoying and things started going crazy. And we learned all stuff about like quadratic formula. We learned all kind of stuff about factoring and solving for roots and all that kind of stuff. That's with the quadratics. And they are obviously not linear because they're in a different category, but you can see that because it kind of goes up quicker. It begins to accelerate, I guess, the slope. But on that note, we learned about another kind of graph that dealt with just that, similar to kind of what's going on right now. Well, luckily, not what's going on, not exactly like what's going on right now, but we talked about that money problem where you're doubling your money every day, or when a lot of things with germs, and they multiply every day. Now, luckily, this craziness is not exponential. It's a different kind of function that you'll get to in Algebra 2, but exponential functions start low and just go on forever. You can also flip and all that kind of stuff, but remember they approach a line called the asymptote. So for the general shape of the graph, I might call that a ramp. You know, a skateboard ramp or a bike ramp. Or a hill, maybe. We kind of talked about going downhill also. So for our equation, we know that's a b to the x. Hopefully you haven't forgotten all this. Or if you did forget it, hopefully it looks semi-familiar. Just visually, you can kind of see it. Fingers crossed. So those are our three types, and that's kind of the first bit of the notes in the CAMU document, if you can see that. And again, if you missed the first little bit, it's fine. I'm going to post this, no big deal. But the brand new thing we're going to be talking about today, and kind of how we're going to connect all these together, is this idea of first and second difference. Now, I'll get there when I get there. So if you look at number 1A, I'll work through this. I only have so much space, so I'm going to have to erase as we go. Luckily, this will be posted, okay? So you can pause, write anything down, that kind of stuff, right? So I want to do this here, so you can ask live questions, or post it so you can pause it whenever you need to. And kind of rewind and go back. So complete the following tables and answer the questions right, it says. Now, this table got some stuff going on. And it has an x table, it has the y is 2x, and then it has this thing called the first diff. Okay, first difference is what it's called. And they recognize it as the first diff. It just means difference. So now I'll get to that in a second. But all of those, 0, 1, 2, 3, it's kind of all the x values we're looking for. Oh, my cat wants in. I have a visitor. A little surprise. He'll come eventually, a couple times, to help me. He's my teaching assistant. Say hello, everybody. Hello, cat. All right. He wanted in the room, so he'll be in the room. So he jumps up on the table. It's not a big deal. X, Y, and this idea of first difference. This is usual. We're used to this. This is new. Okay. This is an X, Y table. So what this says is, if this is our X value, plug it in for X and solve for Y. That's all it's asking you to do. Okay. What it's asking you and wanting you to do is take -3, plug it in for X, and see what you get. So I'm actually going to do that off here on the side. Going to have a 3-column table here. So this helps me sometimes. Anybody? Okay, and that's kind of like saying 2 times, I can write in this column 2 times -3. I can plug in that X value for X in that column. Oh, messed up a little bit. Write the 2 first. 2, 3. Okay, and then on that right column, I can solve that and then rewrite what I get. That kind of helps me out. I'll write it bigger. I think it'll be okay for now. Again, I'm getting used to teaching on camera, so bear with me today, and we'll adjust as we need. But 2 times -3 is -6. 2 times -2 is -4. -2, 0, 2, 4, 6, and so on. That's the 7 values that we want, and that's kind of where we can write here. -6, -4, -2. I'm getting these from this column that I just solved for. Not pulling them out of thin air. I had to plug in -3 for x to get -6. That's how I solved for it. Now this idea of first and second difference is new, and that's what's going to be talking about today. When I say the word difference, there is an operation in math that should come to mind. Sum would be addition, so difference would be subtraction. So what we're going to be doing is looking at the difference between two of the numbers. Again, bear with me. What we'll do is we'll draw a little arrow. What that's doing is pointing to the -6 and the -4. So what we have to ask myself there with this first difference, what is the difference between -6 and -4? It's just going to give me 2. 2 is the difference there. Okay. If I took like -4 minus -6, that would give me 2. Okay. And then you kind of follow the same pattern comparing all of them. So you have to pair up each set. You're going to grab a pair, compare them. And then you're going to use the 4 again. That's fine. Okay? Because you have to compare the 4 and the -4 and -2. And you have to keep comparing every pair that's touching each other. Okay? So you'll start at the top and grab the first 2. And then once you're done with the -6, you'll move down 1, grab the next 2, and compare those difference, compare that difference. And I think we should start to see a pattern. Notice the difference between -4 and -2. Again, it's 2, counting up 2. If we're going from -2 to 0, that difference there is going to be 2. We're starting at -2, go up 1, go up 2, you're at 0. And that pattern kind of follows through there. Okay. So what this asks on the right side is this function is blank. You're going to check one of those boxes. It'll say linear, quadratic, or exponential. Okay. What that wants you to do is use this to identify which type of function. Now, what we could do is we could look at it, and we could look at the equation, and we could say, okay, so it's y equals 2x. That kind of looks like y equals mx plus b. 2 is our m. We have no b. It's all right. And b would be 0, for instance, there. Okay, so we have no b, but m is our 2. So that kind of looks linear. It kind of follows the same general form as a linear equation. But to be sure, we can look at the first difference, and we can use it to identify which type of function. If the first difference is consistent, if the first difference has a pattern, okay, and that pattern is 2 or 3 or -2 or -3. If it's the same number every time, it's linear, okay? So this function, out of our 3 options, is linear. What it's saying is, graphically, see how low I can go over here. I think that graph will pop up. All right. So graphically, what we're comparing, kind of show you what this first difference means. Let me finish labeling the graph here, draw my little arrows. All right. So my blue will be the line here. It'll look something like that. All right. And so what we're comparing is the difference between the y values. So how fast it's growing, the rate of change, you can call it, how quickly it's growing. This idea of rate of change, this kind of compares the rate of change, our first difference. So we've heard that before. We've heard rate of change before, And we've heard rate of change from slope, okay? So the first difference, I'll write it in blue, kind of start over the side here. It counts the rate of change, ran out of room, or slope. I'm gonna have to get used to using a tiny little whiteboard versus the big one and smartboard and stuff. So again, I'll have to get used to organizing all this mess, but we'll get through it. So this first difference counts the rate of change or the slope. All right, and if the slope is consistent, it's always changing by the same amount, that means it's going to be linear. Hopefully that, I'm sure if you have questions, again, throw them in the chat box, that way I can see. The only way I know if you have questions is you put it there. So you can find the chat box and send a message to the whole video or to me or Ms. Tillman, and you can get that question answered for you. What methods can you use to verify this type of function selected? Okay, to verify it, we can do a couple things. We could graph it. All right, we could graph it kind of like what we did. This is a general sketch, and that's fine. You can just kind of sketch it, and you can see that it's linear. There won't be a lot of curveballs in it. It's not going to be super crazy when it comes to the sketching of the thing. It'll be obviously a parabola most of the time, or exponential, stuff like that. So it's pretty obviously straight line. You could have also used a number of things. Graphing is going to be the easiest. You could also check and see which form it falls under. You can see that it's similar to a linear function, y equals mx plus b. Usually it's similar to point slope as well. Or sorry, a slope-intercept form. So we have all that there. That's kind of how we solved that first problem. So luckily, when this is on video, you can pause it and rewind it. You kind of go from there. All right, but I'm going to move on to the next problem here because it's going to add a little bit for the second difference. Okay, again, don't be freaked out because I think it'll be kind of interesting to see. So the beauty of video, you can pause it, immediately email me a question and say, hey, at this time, you said something. What does that mean? All right, cool. I can go back to the video, go to that second, that timestamp, and figure out what question exactly you're asking. Okay, so I think the video aspect will help a lot because it's kind of hard sometimes for me to know exactly what you're talking about. Now, all right, the second difference. All right, again, don't be too freaked out. It's the same idea, but you're doing it twice. So let me scroll. I kind of have the thing pulled up. So what we're going to have to do first is find our values here. A calculator will work, or if you want to do them by hand as well. Again, to do that, all you would do is take the x value and do the operation, solve it for y. What you're actually doing here is all you're doing. Wait, what's the method you use? I used a graph. I just sketched a graph, and that told me, that kind of confirmed that it was linear. Good question. So all you're doing here is taking the x value and you're just squaring it. So what you're doing is -3 squared, -2, don't forget your parentheses, squared, 0 squared, 1 squared, still keep those parentheses, 2 squared, 3 squared. So it's going to be 9, 4, 1, 0, 4, 9. Okay, so I have my y values. That's all of these. That was my first step, so I'll write that out. First step. get the y values. How do we graph it in order to find the first and second difference? I'm going to get there when I do the first and second difference. Megan getting ahead. No big deal. So let me show you what we'll be doing here. So for the first difference, you need to go through each pair. You're going to be repeating using the same number twice a couple times. We'll be looking at 9 and 4 to start. Okay. So you say, okay, what's the difference between 9 and 4? 5. So I always draw your little arrows, you draw your little arrowhead pointing, showing you're comparing the 9 and the 4, and that difference there is 5. Okay. Now what you'll do here is kind of use those two, and you'll compare 4 and 1. Well, the difference between 4 and 1 is 3, right? And now we have these two. Difference between 1 and 0 is 1. If I wanted to go from 1 to 0, it'd be 1 difference, right? Okay, and follow the same pattern, go up there, okay? You'll go from 0 to 1. If you're just joining us, don't freak out. The rest of this will be posted in a minute. So catch on as much as you can, and you'll be all right. You'll be able to catch up if you miss anything. From 0 to 1, the difference there is 1. And then 3, and then 5. Hopefully, we agree there. Okay, so let's look at the second difference. So what we're going to be doing now, the layer we're going to add on to this is compare the 5 and the 3. The 5 and the 3 have a difference of 2. There's a reason we're doing this, the second difference. Because, I guess, let me tell you why. Don't want to leave this out. If the first difference is not consistent, right? 5, 3, 1, 1, 5, 3, it mirrors itself, but it's not the same. It's not like last problem where it was 2, 2, 2, and so on, okay? Because it's not all 2s or all 5s or all 3s or all 1s, that tells me, it tells you, this is not linear. If the first difference is not the same, it's not linear. It's going to be something else. And that something else is going to be either quadratic or exponential. We'll get there, figure out how to determine that. So now let's compare 3 and 1. What's that difference there? I think the difference is going to be 2. Okay. 1 and 1 is 0. We'll talk about that. 1 and 3, I think the difference between 1 and 3 again is 2, and then again is 2. Okay. So this is new, but don't let it scare you. The first difference is not consistent, but absent the 0, so everything other than the 0, the second difference is pretty consistent, right? Now you have to use this to determine which of the 3 it is. So if the first difference isn't consistent, it means it's growing by a different amount each time. So when you go up forever or down forever, something like that. But if the second difference is consistent, so if the second difference spell check me. Then we have a quadratic function. It's kind of one of those things you got to know. if the, how's it going, Jaden? The first difference is consistent, it's linear. The second difference is consistent. We got 2's over here. It's quadratic. And then you can kind of guess if it's not consistent, it'll be growing by a bunch. Exponential, we'll get there when we get there, probably Wednesday. So how do you know? Well, because the second difference is consistent. That's probably what would go in that box right there. What do the first and second differences represent in this function? All right, this is where it gets kind of weird, but fun. It's fine. So stick with me. And if it doesn't make sense for what I'm saying, feel free to YouTube it and look it up elsewhere on first and second differences, and you can kind of Google that kind of stuff and YouTube that kind of stuff. The first difference is going to represent the rate of change. Okay. This is going to sound weird. The second difference is going to measure the rate of change of the rate of change, right? Because we measured how much it's changing along a graph. So if I drew a graph over here, and I had this graph. Okay, it's a little off. Sorry. And I was trying to do rise over run to measure the slope. It would be really, really hard because it doesn't change the same amount, right? It would go, it goes over 1, but up 5, and then over 1, then up 3, then over 1, then or over 1, then down 3. It's not linear, it's quadratic. So it kind of operates by different rules. And that's fine. Okay, that's expected. That's why we learned a whole other rule set for quadratics versus linear, because they operate by different rules for the most part. So what this is measuring is how much the slope is changing. So for what do the first and second differences represent in this function, that's going to be the slope, the rate of change of the slope, how much the slope is changing. Okay. So I had a question there. How do we graph it in order to find the first difference? You don't graph it to find the first difference. You find the first difference by comparing the numbers and like plugging in your x values to the equation that it gives you, and then going from there. If I'm going to get to part C later, we are at the 30-minute mark. I can I will get to that later. I don't want to overwhelm you with a whole bunch of stuff. This is also kind of the test run of Zoom. I will put out an announcement, so be waiting for an announcement on like scheduling and like when to expect Zoom text messages and reminds and links and stuff. You can use this on your phone if you don't want to use that, and if it's better, I can send the link through Remind as well as post it on Canvas. There will be a document corresponding with this, okay? So if you notice on the document, you scroll all the way down, all the way to the back there, identify if they're linear, quadratic, or exponential. You really kind of can't do all that yet because we haven't finished the packet, right? So there might be a question about homework. What's due today? What's due tomorrow? Nothing. Calm down, okay? I realized we kind of did a lot of work for the first 2 weeks of all this online stuff, and thank you for doing your best. I got a lot of messages about being overwhelmed and having too much to do, and your other classes are doing a lot too, and you basically are self-teaching for 6 classes, 5 or 6 classes, and that's hard. So I want to work with you on a good course load and figuring out getting content across without giving you too much to do. So as far as tonight, if you got super confused, you might want to rewatch this when I post it later, or tomorrow, rewatch it and post it. I'm going to be playing with the schedule, figuring out the best time when to have these meetings, and then when to have the meeting again, right? I don't think there's any need for an afternoon session today because there's no practice problems to do yet, right? We have to get to the exponential stuff. So hopefully this will record well and I can post it to Canvas here in a second. I'll probably create another folder or whatever. But if there's any questions about anything, go ahead and ask them now. I'm going to stop recording and work on posting it here in a second.